All right, let's get going today. We're going to start the final exam review. This is the part of the semester when life comes at you fast, and as we're finishing up the midterm exam, we have to start gearing up for the final already. Okay, so if you aren't one of those, if you're not one of the people that obsessively checks CASA's sign-up page, it is available now for the final. So I think it opened up midnight today, which probably means well over half the spots are already gone. But I'm sure there's still a lot left, so please sign up as soon as you can for a final exam seat, May 3rd through the 6th, which is next Wednesday through Saturday. Okay? All right, so we're just going to go ahead and dive right in and get started with the final exam review. Just like we do for other exam reviews, you're welcome to interrupt me with questions, and you're welcome to ask for clarification on any of the topics, even if it's not directly related to the question that I'm going through. And then this will also, of course, be recorded and posted to YouTube. And so we're going to do basically in thirds. We'll try to get through. Thank you. We'll try to get through like about 12 of the questions today, and then 11 each of the last 2 days, and that'll take us through all 34. I still have to post the last batch, but I'll get that done today or tomorrow. All right. So moving to number one. All right. So one of the topics that we learned at the very beginning were the early mass laws. And one concept that comes out of this is our mass ratios. So you do want to know something a little bit about the history and some of the conceptual bases behind some of these early laws. So definitely take some time to review that. But this one is one of the types of numerical problems you might have to do related to this. So we have a sample of iron sulfide, which has an iron sulfur mass of 1.16 to 1, and we want to know how many grams of sulfur are contained in 3.50 grams of the iron sulfide sample. So remember, the idea here is that we can use either mass percents or mass ratios, whatever we're given, as conversion factors between amounts of substances and amounts of the elements that make up those substances. All right, so here we have a 1.16 to 1 mass ratio of iron to sulfur. And so the way to interpret this is that if we were to take 1.16 grams of iron, that would be combined with 1 gram of sulfur, and that's per 2.16 grams of the compound iron sulfide, which we don't know the exact formula of, but we just know the mass ratio. So it's some composition of iron and sulfur. So this 1.6 to 1, which is a sort of a different way of presenting the information, means it's 1.16 grams of iron per 1 gram of sulfur, and then those would combine, of course, to give 2.16 grams of the compound by conservation of mass. So if we want to find the mass of sulfur in this sample, we just have to start with the amount of compound that we're given, 3.50 grams. And then we use those ratios to convert between grams of compound and grams of one of the elements. So we're looking for mass of sulfur, so we see from that ratio there's 1 gram of sulfur for every 2.16 grams of the compound. We could have simplified these numbers and presented it in terms of a percentage or something, but there's really no need to do that. We can just use the raw numbers as they're given, and that converts from grams of compound into grams of the element. Okay, so that comes out to 1.62, which is choice D. Now, we've certainly learned about problems that are way more complicated than this, but don't forget about the basics, and the basics here is that we can combine, when you combine elements to form compounds, they combine in a specific ratio, and the masses of the elements that we combine equals the mass of the compound that's formed, and then we can use those amounts as ratios to convert between them. Questions on that one or any related topic? All right, as I did say, there is some history things on here, so know some of the important names, like the Thompson and Rutherford and Lavoisier, those things that we talked about at the very beginning. Take a quick moment to review those as well, especially the ones in the notes. All right, number 2 is another very early thing we did, which is counting subatomic particles. So we know that each atom is made up of protons, neutrons, and electrons, and we can use the atomic symbol to tell us how many of each that there are. So here we have an isotope, molybdenum-4296. Remember, an isotope is a form of an atom or an element that has a specific mass number associated with it. Different isotopes differ with respect to how many neutrons they have. So the generic form for the atomic symbol that we're given here is this, where X is the symbol. So we're giving you the chemical symbol MO, which tells us that it's molybdenum. And we can go to the periodic table to help us with this as well. And then the two numerical things that go on here, this 96 and this 42, The one at the bottom is probably the easier of the two. It's what we call Z, and it's the atomic number, which is just given by the number of protons in the nucleus. Now we should be aware that this number is not always given to us directly, because if we have the the symbol for the element, in this case MO, we could go to the periodic table to figure out how many protons that corresponds to. So that number 42 would not always be given as part of the symbol. So if we go to the periodic table of elements and find MO, wherever that is, so that's in the transition metals down here. That's number 42. So you can see, it's really hard for me to point to it from this angle, but it's right next to niobium somewhere over there in the transition metals, and it corresponds to atomic number 42. If you can't see that, we'll zoom in a little bit. Alright, so we find MO is number 42, so that tells us that it has 42 protons, whether that part of the symbol is given to us or not. Alright, so we already know right off the bat how many protons we have. The other parameter that's important is this mass number A, which is given as a superscript in the symbol. And that's going to be the number of protons plus the number of neutrons. Alright, so different isotopes are going to have different mass numbers because they have different numbers of neutrons. That's the difference between them. And then for a neutral atom, the number of electrons equals the number of protons. So it's these relationships that we're going to use to figure out how many subatomic particles we have. Alright, so as long as it's a neutral atom with no charge, we just have equal numbers of protons and neutrons. Let me say that again. Protons and electrons to balance out the charge. Alright, so this one is neutral, so we have the same number. Alright, so we have our Z, which is number 42, so that means we have that many protons and electrons. So we have 42 each for protons and electrons, and then the mass number is 96, which is 42 protons plus however many neutrons, which works out to then 54. Alright, so we just subtract the number of protons from the mass number. 96 minus 42, that gives us the number of neutrons. Okay, so the only answer choice that has all of those correct would be A. 42 protons, 42 electrons, 54 neutrons. Okay, questions on that one or anything related? Alright, we're going to just keep plowing through them, make sure we get through all these. Alright, number 3 deals with properties of electromagnetic radiation. What is the frequency and energy of a blue photon with 485 nanometer wavelength? So remember that photons are these little packets of electromagnetic energy that propagate. They have both wave and particle-like behavior. And there's two equations that we need to know that relate the energy, wavelength, frequency, all the different properties of photons to one another. Alright, so the first one is the relationship between wavelength and frequency. So wavelength is the distance between two corresponding points on the wave. Frequency is the number of waves per second that propagate through, and the product of those two is equal to the speed of light c, which is one of the constants that's on our periodic table. So this equation relates frequency and wavelength to each other to that fundamental constant c. Same for any type of electromagnetic radiation. The value of c is the same whether we're talking about radio waves, ultraviolet, infrared, anything like that. The energy is going to be given by another constant h times the frequency. So h is Planck's constant, and this was one of the key developments in early quantum theory, figuring out that the energy of electromagnetic radiation is quantized into little packets of energy that have a value of h times the frequency. And we can rearrange this equation. We basically can combine these two and rewrite this also as hc divided by lambda. So depending on which information you're given, it may be more convenient to use either of these two forms of the equation. Alright, so we need to do a few conversions here. We have 485 nanometers. We want to find both the frequency and the energy of this photon that has that wavelength. So the first thing we have to do is convert the wavelength into meters, because our fundamental constants here, c and h, are in terms of standard SI units. So this would be meters per second. H is in joules times seconds, which is also derived from meters. So you need to have your wavelength always in meters before we start using these equations. Alright, so 485 nanometers, we have to remember the prefixes. Those also come up a lot in the latter half of the course. So nano is 10 to the minus 9, so that means 1 meter would have 10 to the 9th nanometers. Or alternatively, there's 10 to the minus 9 meters in 1 nanometer. Either way, it gives you the same number. So So that gives us 4.85 times 10 to the minus 7 meters. That's going to be the wavelength of our photon in the correct unit. And now we just have to plug this into the appropriate equations up here. So if we want to find the frequency nu, we just rearrange that first equation. It's c divided by lambda. So c is the constant 3 times 10 to the 8th meters per second. We divide that by 4.85 times 10 to the minus 7 meters, and that comes out to 6.18 times 10 to the 14 hertz. Remember, 1 hertz is equal to an inverse second, or a cycle per second. So those units are equivalent. That's usually how we abbreviate it for frequency, is Hz, which is named after the scientist Hertz. And then finally, what we can do is, to get the energy of the photon, we can either take the wavelength that we were originally given and put it into this equation, or we can take the frequency that we just calculated and put it into this simpler equation. So either way will give us the same number. I'll do it the second way. So E is equal to just H times that frequency value that we just calculated. 6.626 times 10 to the minus 34th is the value for H, also on your periodic table. So none of these constants need to be memorized. And then the frequency that we just determined was 6.18 times 10 to the 14th hertz, which is inverse seconds. So that gives us an energy in terms of joules of 4.09 times 10 to the minus 19. All right, so that's the frequency, that's the energy. The only one that works out is choice A. All right, questions on those topics? All right, and remember that these equations do come up in other contexts, because something that I don't think I have in the review, but we should also keep in mind as a possibility, we can calculate the energy for a transition in a hydrogen atom between two energy levels. We had that Bohr equation, and then that energy of the transition is related to the frequency or the wavelength of the photon through these equations. So make sure you know how to use these equations in other contexts as well. Okay? All right, on to number 4. All right, so number 4 is dealing with another important aspect of quantum theory, which is the quantum mechanical nature of electrons. And as we spent a lot of time talking about, and there's a couple more questions that deal with this idea, electrons arrange themselves into what are called orbitals, which are solutions to the Schrödinger equation, and they give us information about the region of space that the electron is occupied from a probability standpoint. They're related to the energy of the electron, all these different things. But one thing that's important about orbitals is that they all have different shapes, and we sort of talked about these shapes also when we were describing the different types of bonds that can form when we overlap these orbitals. So here we have a specific type of orbital. We want to identify which one it is. So remember that we have 3 types of orbitals that we want to know the shapes of. There are, of course, other types of orbitals, but the shapes are way more complicated. So s orbitals are just a simple sphere. It's hard to draw a sphere on a piece of paper, but an s orbital is just a spherical electron density. So that would be the shape. This is clearly not a sphere. Hopefully we can realize that. And then the p orbitals are the ones that are dumbbell shaped. So they have all this basic shape here. The 2 different colors, remember, represent the 2 different phases of the wave function, the 2 different signs for the wave function, although the probability is the same on both sides because the probability is given by the square of the wave function. But that's sort of the shape of a p orbital, which have these dumbbell shapes. And remember, there's 3 p orbitals at any given energy level, and the difference between them is their alignment along the axes. So there's always going to be a px, a py, and a pz orbital that have this same shape, and they're just arranged differently in space. And then finally we have d orbitals, which have 2 different shapes. Most of the d orbitals are 4-leaf clover shape. Alright, so the point is, if we give you a picture of an orbital, you should, at least if it's an sp or d, you should be able to identify it. D orbitals are mostly 4-leaf clovers. Again, they're arranged differently in space. And then the other d orbital, which goes along the z-axis, is this sort of oddball here, which has the 2 different, again, a dumbbell shape but with a donut around it, what we call the torus. All right, so those are the basic shapes. This one is clearly a p orbital. It has this dumbbell shape, so we can eliminate choices B and C. And then remember that, as I said, the p orbitals are aligned along the Cartesian axes, so the name that we give to it is determined by the orientation. This one is clearly oriented along the z-axis, so this would be our pz orbital. Choice E. All right. So there won't be a ton of questions on shapes of orbitals, but you may get one, and so it's helpful to be able to recognize those and understand the differences. Questions on this topic? Yeah. The shading tells you, so your book doesn't really go into the shading. It's not so important for recognizing the shapes, but the shading tells you the sign of the wave function. So all of these are derived from mathematical functions, and they have positive and negative regions. And so the dark color is one sign, and the light color is another sign. What's helpful about presenting the shading is that when you go through and change to the different phase, that's where the nodes exist. We talk about nodes, which are the regions of zero probability. So the p orbital must have a node that goes, it's a plane that goes right through the middle, because as you cross over, you have to change phase when you cross over a node. The d orbital has two nodes that go like this, because every time you cross to a different phase, you have to have a node that's in between them. The other significance of the nodes came into play when we were, or the phasing came into play when we were talking about bonding. So remember that when we form bonds, when you form bonding orbitals, you do in-phase overlap, which means that two of the same color has to overlap. When you do the anti-bonding orbitals, you align them with opposite phases. So the phase is also helpful for understanding how these things overlap to form bonds. But remember that these shapes are really just probability regions, and so the probability is the same regardless of what the color is on both sides. It's a symmetric probability. All right, any other questions? All right, on to number 5. All right, which of the following is an excited state configuration for a phosphorus atom? Okay, so we have to remember that we can predict the electron configurations of atoms using the periodic table, and that's going to tell us the order that the electrons get filled into the different subshells. And the one that we predict from the periodic table is what's called the ground state. All right, so if we want to predict the ground state for phosphorus, that's the lowest energy configuration. We go to the periodic table for phosphorus. We'll see that it has 15 electrons. And so when we arrange these electrons into the correct subshells in order, remember that we start at the beginning. So this is the 1s. So we have 1s2, we have 2s2, then this is the p, so 2p6, 3s2, and then phosphorus is going to be 3p3. Okay, so those are all the electrons for phosphorus. 1s2, 2s2, 2p6, 3s2, 3p3. So that configuration is what's called the ground state. It's the lowest energy configuration for phosphorus. All right, so that's the ground state. Now this question is asking about excited states. Sometimes when I'm talking right at the same time, I read the wrong thing. This is the ground state, and now the question is asking about excited state. And I don't think I spent a lot of time in class on this, which is why I wanted to include it in this review. An excited state is where we take one or more of these electrons from the ground state and we bump it up to a higher energy orbital that's not filled already. All right, so we're going to move one or more electrons to a higher energy orbital. Now we still have to follow the rules, the Hund's rule, well, not necessarily Hund's rule anymore, but Pauli exclusion principle has to be formed. So we can't put 3 electrons in an orbital in an excited state. We still have to follow the rules for quantum numbers, but we're going to take one of these electrons and move it up to a higher orbital that's not already filled. So that's what we're doing for an excited state. And a couple things to keep in mind about excited states is they have the same number of electrons as the ground state. Okay, so we're not going to be adding or subtracting electrons when we form an excited state. That would be forming an ion, which is a completely different topic. And then, as I said, they have to follow the Pauli exclusion principle, which is a maximum of 2 electrons per orbital. So we can't violate that rule in forming an excited state. But they can have a different spin than the ground state, and they are definitely going to have a different arrangement of the electrons into subshells than what you would have in the ground state. All right, so if we look at the answer choices here, choice A is exactly what we found for the ground state of phosphorus. So this is the ground state, it's the correct ground state configuration, but we're looking for an excited state. Okay, so it's not going to be that one. If we look at choice B and C, let's count the number of electrons. So 2, 4, 10, 15. This still has 15 electrons, so it has the correct number of electrons, and we notice that none of the rules are violated because all we've done is taken one electron from 3s and moved it up to 3p. 3s has one electron, which is fine. 3p, which can hold a total of 6 electrons, still only has 4, so we haven't violated any of the rules. So this one works. Choice C also has 15 electrons. And if we take a quick glance at it, none of the rules are violated. So in choice C, what we've done is we've taken both of these 3s electrons and moved them up into 3p. Still a total of 15 electrons and still the correct number of electrons in each subshell. We're not going beyond what is allowed. So that one works out as well. And then finally, choice D, we notice if we count the electrons here, this has 18 electrons. This is the configuration for P3-. Remember that ions are not excited states. This is a totally different species. So that one's not going to be counted as well. So the correct answer is E, which is that 2 of the above configurations are considered excited states. There are basically infinite numbers of excited states you can write for an atom, but it needs to have the same number of electrons, and it needs to still make sure you don't put too many electrons into one single orbital or subshell. Okay, questions on this one? Yeah. They're both excited states, so there's not really a better one. You would predict, I mean, we wouldn't ask you this, but you would predict that this first one is the lower energy excited state because we're only moving up 1 electron, whereas the second one we're moving up 2. So this would be one that's lower in energy, but we wouldn't really ask you that, and they're both valid choices for excited states for this compound or for this element. Yep. Yeah, the 3s orbital is left empty in the excited state. Because in the excited state, we're taking one of these electrons from the ground state and moving it to somewhere else that's higher in energy. So you can have empty subshells that are totally skipped in an excited state. That would never happen in the ground state, but it can certainly happen for an excited state. Anything else? Okay, on to number 6. We make sure to keep moving. All right, which of the following is a valid set of quantum numbers for an F electron? All right, so remember that quantum numbers are these numerical parameters that define electrons in atoms, and they're related to various aspects of the wave function, various aspects of the Schrödinger equation, which we're not going to give you, the mathematical details of, but these things tell you different properties of electrons in orbitals. So we have a set of 4 quantum numbers here. We have N, L, M sub L, and M sub S. I'm going to keep, at least in a little bit of detail, what these different things mean. So N is the principal quantum number. It's the size and the energy of the orbital. So the higher value of N corresponds to a larger orbital, and the higher value of N tells you that it's at higher energy as well. And N can have any integer value from 1 to whatever, 1, 2, 3, 4, and so on. L is the angular momentum quantum number, which gives us the shape of the orbital. So different orbitals that have different values of L have different shapes. We talked about the shapes earlier, S, P, D, and then there's also F. Those are distinguished by the different values of L that they have. It also contributes to the energy when we have multiple electrons. So for multi-electron atoms, the second quantum number L also is a determinant for the energy of that electron. M sub L, which is the third one, tells us the orientation of an orbital. So when you have px, py, and pz, as we talked about, those differ with respect to the value of M sub L. There's not really a one-to-one correlation between the value of M sub L and the orientation, but suffice it to say that the value of M sub L will relate to the orientation of that orbital in space. And then finally, M sub S is the last one, which is a property of an electron and not an orbital. And it has either value plus 1/2, minus 1/2. It's what we call the spin of the electron. It only has 2 possible values. So those are all the quantum numbers. And when we ask you about, here we're specifically asking about an F electron, that letter that we often give for subshells, the S, P, D, F, and so on, that is again determined by the second quantum number here. So for these different values of L, we have different letters associated with them. The ones that we're going to see most often, which occur in real atoms, are going to be 0, 1, 2, and 3, which corresponds to S, P, D, and F. Now you can go higher than this if you wanted, but really the ones that you're going to see in real atoms are these 4. So if we have an F electron, that means L equals 3. So the first thing we can do is we can cross out any answer choice where the second quantum number L does not equal 3. So that gets rid of this one and this one. Both of these have the wrong value of L, so we don't even have to think about the rest of the quantum numbers for those ones. But for choices A, C, and D, they all have the correct quantum number, or they all have the correct value for the second quantum number, so we need to see which one of these the other ones work out. So remember that the rules for quantum numbers are that L is equal to 0, 1, 2, all the way up to n minus 1. So that means if we have an L equals 3 orbital, which is what we have for an F electron, the smallest value of n has to be 4. So we're only going to see L equals 3 in subshells where n is greater than or equal to 4. If n equals 3, we can't have L equals 3. That's not allowed by this rule. So this first one here we can now cross out because this has an invalid value of n, so that one's not going to work. And then finally for choices C and D, the only difference between these two is the value of m sub L. So if we remember the values that are allowed for m sub L, it's going to be minus L, including 0, all the way to plus L. So that means for an F orbital, the allowed values are going to be minus 3, minus 2, minus 1, 0, 1, 2, and 3. So choice D doesn't work because it has this value minus 4 for m sub L. So the only one where all 4 quantum numbers check out is choice C. It has a value of n that's allowed for L equals 3, and it has a value of m sub L that's allowed also for an L equals 3 orbital. All right, so any questions on quantum numbers or the rules that they follow or what they mean? Yes, sir. Well, the spin can be either plus 1/2 or minus 1/2, and so as long as it's one of those two values, it's a valid set of quantum numbers. There's no real difference between plus 1/2 and minus 1/2 in determining the energy of an electron. By convention, we usually put electrons in plus 1/2 first, and then we would start adding a minus 1/2, but there's no real difference if you did it opposite to that. So as long as the value of m sub s is either plus 1/2 or minus 1/2, that would be a correct set of quantum numbers. In this case, they're all plus 1/2, so we don't even have to distinguish those. But it doesn't have to be plus 1/2. If this had been minus 1/2, it would have still been an okay answer choice. Okay? All right, number 7. All right, so we do have a problem on this, so that's I didn't realize I had this in here. A hydrogen atom undergoes a transition from n equals 4 to n equals 2. What is the wavelength of the photon that is absorbed or emitted? Okay, so remember the idea here is that the Bohr model assumes that we have quantized energy levels for hydrogen that are determined by the value of n. So they go up as we increase n, and they get closer and closer together also. Alright, so the ground state is n equals 1. That's where the electron is going to be in the ground state. We can also have excited states with different values of n, and then we can have an electron moving between different energy levels. And whenever that happens, anytime an electron moves between energy levels, a photon is either going to be absorbed or emitted. In this case, we're going from n equals 4 to n equals 2. So we're starting here, and we're doing this transition, which means that a photon is emitted. Whenever the energy level is getting lower, whenever we're going from higher n to lower n, that means the energy of the electron is decreasing, and that excess energy is given off as a photon. So we're emitting a photon whenever we go from higher n to lower n. So the first part of this question, we have to realize that the photon is emitted, so we can cross out a bunch of answer choices now because A and C say that the photon is absorbed. But if we're going from higher n to lower n, no matter what the value of the wavelength is, it must be a photon that's emitted anytime we're decreasing the energy level. Alright, so now let's figure out what the actual wavelength is. So the equation for this is the Bohr equation. Delta E, which is the change in energy for an electron, is equal to minus 2.18 times 10 to the minus 18 joules. It has a term for the atomic number Z, but we're only going to do this for hydrogen, so that's always 1, and then it's going to be 1 over nf squared minus 1 over the initial value squared. So these are the two values of n that the electron is moving between, so it's going to be 4 and 2 for these ones. So if we plug in the numbers, minus 2.18 times 10 to the minus 18 joules. Nf is the final value of n, which we're going from 4 to 2, so n equals 2 is the final value. If you switch these, the only thing that'll change is the sign of delta E. You'll still get the right value for it, but the wrong sign. And the initial value is 4. So we get minus 4.088 times 10 to the minus 19 joules. So that's the change in energy for the electron. And then the energy of the photon that's given off is going to be equal to this value, but just the absolute value of that. So the energy of the photon that's accompanying this process is going to be equal to that absolute value. And as we saw earlier, the equation for the energy is hc divided by lambda. So we can get the energy of the photon. When we have this equation, we can solve for lambda. So lambda is equal to h times c divided by the absolute value of delta E. You never have negative photon wavelengths or photon frequency, so if you got a negative number out of this, then you should just change the sign and you'll be done. All right, so we have 6.626 times 10 to the minus 34 is h. 3 times 10 to the 8th meters per second is c. Those are those fundamental constants that we've already used. And then the energy that we calculated was 4.088 times 10 to the minus 19 joules. All right, so when we put all those numbers in, we get 4.86 times 10 to the minus 7 meters. All of the answers are in nanometers. We multiply that by 10 to the 9 to get 486 nanometers. All right, so 486 is the correct answer, and it's an emitted photon because the energy level is decreasing. All right, so if we had asked you for the delta E, you would need to include the sign. Once we're converting that delta E into a photon energy, whether it's absorbed or emitted, the photon is just going to be dependent on the absolute value of that energy difference. Any questions on that? All right, number 8. Here we're comparing sizes of atoms or ions. Select the largest from the following list. So when we're considering the sizes of atoms, remember that we have a periodic trend that's pretty regularly. The size increases as we go right to left on the periodic table, and it increases as we go top to bottom. That works for neutral atoms, but here we're dealing with ions as well. So when we're dealing with ions and atoms together, or just ions, the first thing we need to think about is how many electrons do they have? What is the electronic configuration? So if we look at the first four, calcium 2 plus, potassium plus, argon, Cl minus. If we go to the periodic table and find those, calcium 2 plus, calcium is here, so calcium 2 plus has 18 electrons. It has the configuration of argon. K plus also has 18 electrons, has the configuration of argon. Cl minus has the same number of electrons as argon. So those first four atoms and ions all have the argon configuration. So these are called isoelectronic when they have the same number of electrons. However, if we go to choice E, which is Br minus, that's one down on the periodic table. So this one has the configuration of krypton. All right? So it has a different number of electrons. So we can first compare choices A through D because they're isoelectronic. That means they have the same number of electrons. And when you're comparing isoelectronic species, the more negative charge they have, the larger they are. All right, and that's because the ones that have more negative charge have fewer protons in the nucleus, so they're pulling the electrons not as tightly, and so they're going to be farther away. So in this set of ions, the one that's going to be the smallest is calcium 2 plus, that has the most positive or the least negative charge, and then K plus, and then argon, and then Cl minus. All right, so of these first four, Cl minus is the biggest because it has the most negative charge. Now we need to compare Cl minus to Br minus, and the difference here is that they're in different rows of the periodic table. Cl minus is in the third row, Br minus is in the fourth row. Maybe I had it backwards, fourth and fifth. Either way, Br minus is below Cl minus in the periodic table, so it's going to be larger because atomic radius or ionic radius increases down a group. And sometimes it's helpful to think about the magnitude of these differences. So if you go right to left or left to right on the periodic table where you're comparing things that have all neutral charges, the effect on the radius is pretty subtle. The bigger effects on the radius are when you add and remove electrons, the radius changes by a lot, so that's a bigger effect. And as you go from top to bottom on the periodic table, that's also a bigger effect than moving right to left. So that's helpful to keep in mind for some of these as well. But in this case, very clearly, Br minus is going to be the biggest one, which is what we're asked for in this problem. So the largest one is Br minus. It has the most negative charge, and it's the furthest down in the periodic table. So very clearly, it wins out. Okay, questions? All right. On to number 9. Number 9 deals with ionization energy. Which of the following is expected to have the smallest ionization energy, and we're talking about the third ionization energy, i.e. 3. So we've used ionization energy a lot, especially recently when we started talking about lattice energies. We use that in there as well. So the ionization energy is going to be defined as removing an electron. So we have a neutral atom in the gas phase, and we remove one electron to form a gas phase cation. So this is the first ionization energy, i.e. 1. i.e. 2 is just removing the second electron. So we take the positive ion, we remove one more electron. That's defined as the second ionization energy. And then finally, the third ionization energy would be the 2 plus cation going to the 3 plus cation with one more electron being lost, and so on. Alright, so we have successive ionization energies for every atom, which refers to removing one additional electron each time. They always increase as you go higher and higher. So for any atom on the periodic table, the first ionization energy is the smallest, the second is bigger, the third is bigger, and so on. And you're going to see a very large jump in the ionization energy when you start removing core electrons. So the valence electrons are comparatively easy to remove, and then the one you're going to have a huge jump in ionization energy when you start removing core electrons. So if we look at the first answer choice, sodium, the electron configuration for sodium is going to be, its neon is the noble gas that comes before it, and then it has a 3s1 valence electron. Alright, so sodium is neon 3s1. Come on. This has one valence electron. So if we're talking about the third ionization energy, we're already removing a core electron for sodium, because for sodium, after the first ionization, we're already into the core electrons, and so those are going to be extremely difficult to remove. So this is expected to have a very large third ionization energy. And then if we look for boron and aluminum, those both have configurations. This is going to be 1s2, 2s2, 2p1. And this one has the same valence configuration, just one down in the periodic table, 3s2, 3p1. Alright, so boron and aluminum are right on top of each other, and these both have 3 valence electrons. So remember, the valence electrons are both the s and the p in the highest shell. So these both have 3 valence electrons, which means they're both for ionization energy 3, you're going to be still removing that last valence electron for that ionization. So that one's expected to be smaller. And then finally, magnesium and calcium. Magnesium is neon 3s2, argon 4s2 for calcium. Both have 2 valence electrons, which is they're expected to have a large third ionization energy. So if we're looking for the smallest third ionization energy, we want to find the ones where we're still removing valence electrons. And so for both of these, for the third ionization, we're still removing the last valence electron. So which of those two is the smallest? So we expect that boron is going to be larger than aluminum because we're comparing the same ionization energy, and ionization energy increases as we move up. Alright, so the smallest one would be then aluminum, because we're removing valence electrons, and it's going to be smaller than boron because it's lower on the periodic table. Alright, so that didn't deal directly with the trends for first ionization energy, but we had to think also in this case about the number of valence electrons and whether we're removing valence or core electrons. Questions on that one? Alright, we have a couple more to get through, so let's go along. Alright, the formula for the oxide of gold is Au2O3. Which of the following is the formula for gold hydrogen carbonate, assuming the gold has the same charge as the oxide? Alright, so this is just dealing with formulas for ionic compounds where we have to write out the charges of the two ions and then make sure that they balance each other. Make sure that the positive charge is completely canceled out by the negative charge for the anion. So we're starting with Au2O3. We have to use this to determine what the charge is on the metal center. Because oxygen is always going to be -2. Oxygen is here in the periodic table. It gains 2 electrons to get to the noble gas. So anytime oxygen is an ionic compound, it will have a 2- charge. For the nonmetals, the charges are invariant. You have 3- charge for nitrogen, 2- for oxygen, and anything else in the same column, 1- charge for all the halogens, and so on. So oxygen has a 2- charge. In this compound, we have 3 of them. So we have a total of 6 minus charges from the anion. And then the gold that's in this formula, we have 2 of them, so that each gold has to be 3 plus to balance the 6 minus charge. So in this case, the gold has a 3 plus charge. We used the formula of the oxide to determine that. And it's going to be paired with the hydrogen carbonate anion. So remember that a lot of our polyatomic anions, carbonate, phosphate, and so on, they have their basic charge, and then you can add 1 or more protons to those. So if we have carbonate, which is CO3 2 minus, for hydrogen carbonate we just add 1 H plus to that. So the formula would be HCO3, and instead of a 2 minus charge, it now has a 1 minus charge, because we've added an H plus to this. So the hydrogen carbonate has the formula HCO3, and it has a 1 minus charge. And then so if we want to balance the charges to get the formula of this compound, remember that we take the charges and we turn them into subscripts. So this one would then work out to be 1 gold with 3 hydrogen carbonate anions to balance the charge. And so the one that works there is choice C. Alright, so if you've completely forgotten them in the last few months, review the polyatomic ions and their charges, and make sure you know how to then balance the charges when forming formulas for ionic compounds. Okay, questions on this? Alright, now here comes our favorite, calculating the lattice energy. So we have a hypothetical ionic compound, M2X. There will be a lattice energy question on the test, just one, but make sure you know how to do it. It could either be calculating lattice energy, or it could be comparing lattice energies of different compounds, so kind of know both aspects, but there will be one question about it, so consider this your fair warning. And we have all this information. We have ionization energy, we have sublimation, all these different things. We want to calculate lattice energy. Now, what I think is helpful, I went through the cycle in class, the Born-Haber cycle, where we start and end at the ionic compound, consider all the individual steps. It's helpful for you to know that, to understand it. There is an equation we can use, though, that is also going to work just about every time. So if we have an ionic compound that has this formula, M with some subscript, X with some subscript, for the types of compounds we're going to calculate lattice energy for, these are all either 1s or 2s, so those are really the only 2 values. If we have M2X, which is the compound we're talking about here, that means M equals 2, subscript M is 2, and the subscript N equals 1. And then the equation for lattice energy is, we start with a delta H of formation for the compound. So whatever the compound is, we use this delta H of formation. We subtract 2 terms for the metal, modified by whatever the coefficient or the subscript is for the metal. So M times the delta H of sublimation for the metal, which is the energy for going from the solid to the gas phase. That's for the metal itself. And then we subtract M times the ionization energy, also for the metal. So we have those 2 terms for the metal that we account for. And then finally we have 2 terms for the nonmetal. So if the nonmetal exists as X2, this is where if the nonmetal is diatomic, which is the case for most compounds except for sulfides where it's S8. If we have a diatomic nonmetal, we're going to use N over 2 times the delta H of dissociation. That's the energy to break the bond of X2. And it's N over 2 because we want to have N X's, and so N over 2 times X2 gives us N X atoms. And then finally, minus N times the electron affinity, also for the nonmetal X. So we have these 5 terms that we have to combine to get lattice energy. So the delta H of formation for this compound is given directly. It's the formation of the compound from the elements, and is minus 335. The value of M, the coefficient for, or the subscript for the metal is 2, so we're going to take 2 times the sublimation enthalpy. Sublimation is that second number there, 79 kilojoules per mole. 2 times the ionization energy, which for the metal is 525. And then we have N over 2, so N is equal to 1 for this compound, because there's only 1 X in there. So 1/2 times the dissociation, which is 178 kilojoules per mole. That's the one that corresponds to converting x2 into 2x's, so that's that energy there. And then minus 1 times the electron affinity. Here it's a combination of two electron affinities because x is forming a 2 minus anion, but we just use that number as is given to us, 123. Come on. And so those are the numbers that we put in, and we get minus 1755 kilojoules per mole. A lot of these are numerical problems, so you'll just enter in the number. Should always be negative, so if you don't get a negative number, check yourself and check what you did, and that's what you get for this. So this equation here is going to work almost every time unless it's a metal sulfide where the standard state for sulfur is S8, and it could be one of those. But for the rest of them, you can use this and just plug in the numbers. Okay, any questions on that? This is one you're just going to have to practice. It didn't come up on the third midterm, but try to do a few of these before the final to get the hang of it. All right, the last one we'll go through today is number 12, which is about different types of bonding. So which of the following elements or compounds, I should say elements or compounds, because copper is not a compound, which of these are matched correctly with their bonding type? All right, so remember that we have basically three types of bonds. We have covalent, ionic, and the one that we've learned most recently is metallic bonding. All right, so three basic types of bonding, and we have to recognize when these occur. So covalent bonding occurs when you have nonmetals only, either as elements or combinations of nonmetals. Those are going to form covalent bonds. Ionic bonds is going to be a metal with a nonmetal. As we just talked about, when metals and nonmetals combine, they form ionic compounds. And then finally, for metallic bonding, you have just a metal by itself. Or there are what are called alloys, which are two different metals combined, but you only have metals when we're talking about metallic bonding. So if we look at the four choices here, FeCl3, iron is a metal, chlorine is a nonmetal, so this one would be ionic, so that one's correct. Copper is a metal, so copper should be metallic bonding, because it's a metal by itself, so that one's incorrect. SOCl2, sulfur, oxygen, chlorine are all nonmetals. Remember, nonmetals are on the right side of the periodic table, and metals are on the left. Those are all nonmetals, so that's going to be covalent. So that's correct. And then finally, the one that might be a little bit tricky here is aluminum chloride, AlCl3. If we go to the periodic table, aluminum is here in the P block, but it's to the left of that imaginary staircase that runs down. So aluminum is a metal. You definitely want to remember that aluminum, gallium, indium, these ones, even though they're in the P block, they're metals. So there are some P block metals. Aluminum is classified as a metal. You've all seen aluminum foil, so you know that it's shiny and all that stuff. It looks like a metal, so no surprises there. So aluminum is a metal, so that means that aluminum chloride is technically classified as ionic bonding. So that one's going to be wrong as well. And so the ones that are correct are 1 and 3, which is choice D. So this leads into some of the stuff we talked about also in Chapter 9 with the different types of solids that can form. At a basic level, the type of bonding can be predicted just by considering the types of elements that make up the compound or the element. All right, that takes us to the end of the first part. We have parts 2 and 3 coming up later. And so I'll see you guys on Friday.